Good day, everyone. This is Dr. MAMTamayao-Kieke, and today we're going to tackle Unit 2-3, which is about blocking and confounding in the 2 to the k factorial design. In particular, for this lecture, we're going to talk about blocking a replicated 2 to the k factorial design. And after that, we will proceed to confounding in the 2 to the k factorial design. And we will talk about confounding in 2 blocks, 4 blocks, and in 2 to the p blocks. And lastly, we're going to tackle partial confounding. So let's first talk about blocking in a replicated 2 to the k factorial design. And let's talk about the motivation for blocking in a factorial design. As you can see here, there are 2 main bullet points, and these represent the two of the main motivations why there is a need for blocking in a factorial design. The first one is when resources are not enough, okay, to allow all the runs in the factorial experiment to be run under homogeneous conditions. For example, when you have a batch size of raw materials that is not large enough to make all the runs in a replicate. Now, the second motivation could be when you want to deliberately vary the experimental conditions in order to represent situations that are likely to be encountered in practice. So, an example of this is the use of several batches of raw materials of varying quality if it is known that raw material quality vary in practice. Now, having said that, how do we actually perform blocking in a replicated 2 to the k factorial design? Well, it's actually the same method as in any general factorial design in blocks. And for this, recall the previous discussion on blocking under Unit 2-1 and Unit 2-2. Okay, and the non-homogeneous conditions are actually represented by the blocks, and one replicate would be run in one block. Therefore, the number of blocks is equal to the number of replicates, and you would be happy to note that the analysis is actually similar to any blocked factorial experiment. So you are already familiar with that. Okay, so let's take the example, okay, the previous example on chemical process yield, which is a 2 to the 2 design, okay, and let's see how we can modify, and let's see how the approach for this 2 to the 2 design would change, okay, with blocking. Okay, so as you can see here, the familiar table with observations for the 3 replicates for the different treatment combinations for factor A and factor B. Okay, so the modification here is suppose that raw material batch size is only large enough for 4 trials to be made. Okay, so you can only run 4 trials for each batch size. For this situation, we need 3 batches of raw materials to run the experiment. Now, with the 3 batches of raw materials, there could be some variation across the batches. Therefore, it is logical to block, okay, with respect to the raw material batch. And we can treat each replicate, okay, we can run each replicate in one block, okay, because the batch size is enough to run all the treatment combinations for one replicate, or we can completely run the replicate in one block, okay, and then the second replicate as block 2 and the third replicate as block 3. Okay, now we're going to need the sum of observations for each block later on. So we note that the sum for block 1, denoted as B sub 1, is equal to 113. Block 2 is 106, and block 3 is 111. Recall this table. This is actually the original Anova table for the original version of the chemical process yield experiment. So this is the result for the design, 2 to the 2 factorial design without blocking. Now with blocking, as you can notice here, we have an added row, okay, to show the sum of squares, the degrees of freedom, and the mean square for the blocks. Okay, and yes, you can see there are 2 degrees of freedom for blocks, okay, because we have 3 blocks, okay, and these are the sum of squares. I will talk about this later on, and as usual, mean square is just equal to your sum of square divided by your degrees of freedom. Now note that the mean effects and the interaction effect, the values for these are actually the same as in the previous table, okay, as if there is no blocking. Okay. The only values that varied here are actually that for the blocks and the error. And to compute for the sum of squares of the blocks, we just take, okay, the square of each sum of observations per block divided by 4, okay, for all blocks, and subtract the square of the grand total divided by 12. Okay, now the error, as you can see here, is now, and this is actually equal to the sum of squares without blocking minus the sum of square of the blocks. Okay, now let's proceed to confounding in a factorial design. Okay, now recall that blocking in factorial design is done when, well, one, when we cannot have all the runs be under homogeneous conditions, or when we want to deliberately change the conditions to represent what is happening in reality. And so far, what we've talked about is blocking where we can run a complete replicate in one block. Okay. Now, the motivation for confounding in a factorial design is when resources are not enough for a complete replicate, okay, to be made in one block. All right. So if we cannot run all the treatment combinations, okay, for one replicate in one block, then we do confounding. Okay, so when block size is less than the number of treatment combinations in one replicate, then it is necessary, or one method that we can adopt is confounding the factorial design. Okay. Oh, by the way, when block size is less than number of treatment combinations in one replicate, this is also referred to as incomplete block design. Okay, now what are the implications of confounding in factorial designs? Well, one, information on certain treatment effects, in most cases high-order interactions, is indistinguishable from the blocks. Okay, and we can also call that is indistinguishable from the blocks, or that is, the information is confounded with the blocks. Okay, is hidden by the blocks. Now, 2 to the k factorial designs can be run in 2 to the p incomplete blocks where p is less than k. Okay. Now, if we have p is equal to 1, then we have 2 blocks, p is equal to 2, 4 blocks, and then p is equal to 3, 8 blocks, and so on. Okay, now in each incomplete block, then you would have 2 to the p observations. Okay, so let's proceed with the method of analysis and the construction of blocks in 2 to the confounding the 2 to the k factorial design, first in 2 blocks. Okay, so consider this case where we want to consider the case of a 2 to the 2 factorial design. Okay, and as you know, in a 2 to the 2 factorial design, we have 4 treatment combinations. Okay, so these are the treatment combinations. Now, what if your raw material, okay, your raw material is only enough to run 2, okay, 2 combinations. So say, for example, 1 and A, okay. that means you would need another batch of raw material to run the rest of the combinations. And in this case, you would need two blocks, okay, two blocks to run the complete replicate. All right. And of course, note that the order in which the treatment combinations are run within a block should be randomized. And the order in which the blocks are run, okay, is also randomized. Okay, so this is familiar to you. This is the 2 to the 2. Well, on the left side, you have the geometric representation of a 2 to the 2 factorial design. And in this particular case, okay, we have a confounded, 2 to the 2 factorial design run in two blocks. Okay, and the solid dot represents the treatment combinations that would be run in block 1, and the hollow dots are run in block 2. Okay, and say this could be an example assignment of the 4 runs to the 2 blocks. So say, for example, in block 1, we have 1 and AB, and block 2, we have A and B. And we will talk more about construction of blocks later on. Okay, but before that, let's talk about the effect estimates. Okay, now in the unblocked design, recall that this would be the equations that you would use for estimating the effects, okay, for the factorial experiment. And this is the equation for obtaining the interaction effect estimate. Okay. Now, if you refer to the block assignment that I showed you earlier, okay, you will notice that in these equations, okay, there would be 1 plus and 1 minus sign in each block. Okay, so for example, in this case, remember that in block 1, you have 1 and AB. In block 2, you have A and B. Okay, in this equation, you have a plus sign for A and a minus sign for B, and same is true with the equation for the effect estimate for factor B. Okay, now when we look at the interaction effect, okay, you can see that 2 treatment combinations with plus are in one block, okay, and 2 minuses are in the other. And so with this, the block effects are indistinguishable for the effect estimate of A and B. However, for AB, it will be confounded. And then if you look at the plus and minus table for A, factor A, B, and the interaction AB, okay, you would see that the plus signs under AB fall under one block, which is block 1, and then the minus signs fall under the other block, which is block 2. And as I mentioned earlier, AB is actually confounded with the blocks. Okay, now let's look at the table of plus and minus signs for the 2 to the 3 design with 2 blocks. Again, to further understand the concept of some of the effects or interaction effects being confounded with the blocks, okay, as well as understanding better how to construct the blocks. Okay, so let's look at this. You can see here the plus and minuses for the different factors and their interactions. Okay, now you know how to construct this table. You know that a plus would basically mean a high level of a factor in each of these treatment combinations, and a minus would mean low level. And then for the interactions, it's basically just the product of the signs for the corresponding factors, mean factors. Negative times negative would be positive, positive times negative would be negative, and so on. And then, of course, you can do the same for ABC. And for these different effects and their interactions, none would correspond exactly with the different blocks. Okay. Okay, so for the 2 to the 3 design, it is recommended to confound the blocks with the highest order interaction, because in most cases, they would be negligible. So in this case, we have ABC, okay, and we have the blocks corresponding to the two signs, which are plus and minus, and then we assign the treatment combinations to the blocks. And this is just the summary of the block assignments. This is a geometric representation, and this is another figure to show the assignment of the 8 runs to the 2 blocks. Okay, now there are of course other methods for constructing a block, and this would come in handy, especially when you have larger numbers for larger values for k, or you have more factors. Okay, and the first one that we're going to talk about is block generation using the linear combination. Okay, and this is for the 2 to the k factorial design. Okay, now this is the linear combination corresponding to a 2 to the k factorial design, and this is actually called the defining contrast. Okay, so L is equal to alpha 1 x1 plus alpha 2 x2 up to A sub k, alpha sub k times x sub k. And x sub I is equal to the level of the I factor appearing in a particular treatment combination. For low level, it's 0, and high level is equal to 1. Alpha I is equal to exponent appearing on the I factor in the effect to be confounded. Okay, and this would be 0 or 1. Okay. Now, treatment combinations with the same value of L modulus 2 would be assigned to the same block. Okay. So, to illustrate the use of the linear combination, okay, let's take the case of 2 to the 3 factorial design. Okay. So, for this case, it is recommended again that the highest order interaction would be confounded with the block. So, for the 2 to the 3 factorial design, it would be the ABC, okay, interaction that would be confounded with the blocks. Okay, therefore, since we have all the factors, okay, alpha I would be equal to 1 for all I. Okay, and the defining contrast, okay, would be x1 plus x2 plus x3. Okay. And so, using this defining contrast, we can generate, okay, the values of the expressions for L, okay, for the defining contrast corresponding to the different combinations, okay, and then take L modulus 2, all right? So, for example, we have here the treatment combination where A, B, C are at their low level, okay, so and this can be represented by 0, 0, 0. A is represented by 1, 0, 0 because it is this treatment combination corresponds to that combination where we have a high level of A, okay, and then low levels of B and C. Thus 1, 0, 0. And then B would be 0, 1, 0, denoting that we have high level of B and low levels of A and C, and so on. Okay, now using these numbers, we just plug them in. We just plug them into the defining contrast equation. Okay, and so we have 1, okay, times 0 plus 1 times 0 plus 1 times 0. Okay, and this would be equal to 0, and L modulus 2, okay, 0 modulus 2, okay, and we get L modulus 2, all right? Now, for A, we have L is equal to 1 times 1 plus 1 times 0 plus 1 times 0, and this would be equal to 1, and so on, okay? Now, using this method, okay, we would generate 2 groups of combinations, okay? And one group is consists of those combinations with the same L modulus 2. So in this case, you have 1, AB, AC, and BC have the same L value for L modulus 2, which is 0 modulus 2, while A, B, C, and ABC all have 1 modulus 2. Alright? Therefore, block 1 would contain A, B, C, and ABC. Block 2 would contain 1, A, B, and BC. Now, remember to randomize the order at which the block is run. Okay, so it doesn't matter which one. You should actually randomize which one would be run first, block 1 or block 2. And then, you should also randomize the sequence of treatments within each block. Okay, now let's talk about the concept of the principal block, okay, in a 2 to the k factorial design. The principal block is simply the one that contains the treatment combination 1, okay, or the treatment combination where all the factors are at their low level. Now, what makes it special? It actually has some interesting and useful group theoretic properties. Okay, and one being that the group is formed, okay, the group is formed with respect to the multiplication modulus. That means that any element, okay, except for 1, can be generated by multiplying any other 2 elements in the principal block modulus 2. Okay, and the second interesting property is that the treatment combinations in the other blocks can be generated by multiplying each element in the principal block by 1 element in the other blocks. Now, as k becomes higher, you will realize that these properties are actually very helpful. Okay. We will illustrate further how these properties can be made handy in block generation in the succeeding discussion. Okay, but first let's talk about estimation of error. Okay, and let's first look at the cases where k is less than 4. Now, when k is small, okay, where k is less than 4, for example, it is necessary to replicate in order to get an estimate of the error. Now, suppose you have a 2 to the 3 factorial design and it will be run in 2 blocks, okay, and is replicated 4 times with ABC confounded. Okay, so this is how it would look like. So this is a 2 to the 3 factorial design run in 2 blocks with ABC confounded and which has 4 replicates. All right, so replicate 1, replicate 2, replicate 3, and replicate 4. So you will note that the same combinations are run, okay, in a block for all the replicates. Okay. But of course, you have to remember that the order in which the combinations are run should be randomized. Now, for 2 to the 3 design with ABC confounded with 4 replicates, this table shows an information on the analysis of variance, okay, and in particular, the sources of variation and their corresponding degrees of freedom. Okay, and as you can see here, okay, these are the sources of variation. You still have your main effects and your 2-factor interactions. Now, in this design, you have ABC confounded with a block, okay, and we have 8 blocks. And because we have 8 blocks, we have 7 degrees of freedom, okay, and the distribution of the degrees of freedom, okay, actually corresponds to 3 for the replicates, okay, 1 to the block, okay, or ABC, okay, the interaction of ABC, and then 3, okay, for the error, okay, error for ABC, okay, and for the error, we have 18 degrees of freedom, and it's usually safe to say that interaction between the replicate and effects are 0, and the resulting mean square is equal to the estimate of the error. Okay. Now, in the case that circumstances allow replication of confounded designs, it is generally better to perform partial confounding. And this is going to be the last section of our lecture today, but do take note that that is one of the uses of partial confounding. No? In partial confounding, okay, you confound a different effect in each replicate, okay, and then the result will, and because of this, the result will provide some information on all the effects. So when your k is greater than or equal to 4, okay, that is when it is moderately large, okay, only one replicate can usually be afforded. Now, higher order interactions can usually be assumed to be negligible, and their sums of squares are combined as errors. Now, the normal probability plot of factor effects will come in handy in this case. Okay, now let's take again another example to illustrate some of the concepts that we've discussed so far. And let's go back to the example on filtration rate of a chemical product. Okay, so for easier reference, I copied it here. Okay, this is the original example. A chemical product is produced in a pressure vessel. A factorial experiment is carried out in a pilot plant to study the factors thought to influence the filtration rate of the product. The four factors are temperature, denoted as A, pressure, noted as B, concentration of formaldehyde, denoted as C, and stirring rate, denoted as D. Each factor is present at two levels. Now, the design matrix and the response data obtained from a single replicate of the 2 to the 4 experiment are shown in the succeeding slide. Okay. Now, the 16 runs are made in random order, and the process engineer is interested in maximizing the filtration rate. Now, current process conditions give filtration rates of around 75 gallons per hour. The process also currently uses a concentration of formaldehyde, factor C, at high level. The engineer would like to reduce the formaldehyde concentration as much as possible, but has been unable to do so because it always results in lower filtration rates. Okay, so now these are the combinations. Okay, these are the combinations, these are the factors, okay, and these are the observations. So we only have one replicate. Okay, and this is a geometric representation of the observations. Okay, so now let's modify the example to illustrate the use of a confounding in factorial experiment. Okay, so suppose that one batch of raw material cannot accommodate all treatment combinations. So you cannot completely run one replicate in one batch of raw material. Okay, now furthermore, only 8 treatment combinations can be run from a single batch of raw material. Recall that we have 16 runs, all right? So you need 2 batches of raw materials to run a complete replicate, basically. Okay. So in this new experimental design, you have a 2 to the 4 design confounded in 2 blocks in order to complete the runs. Okay. Now, confounding the highest order interaction ABCD with blocks is of course logical because in most cases, the highest order interactions are negligible. Okay, now what is the defining contrast? Okay, remember that this is one method to generate the blocks. Okay, but let's use the defining contrast. Okay, so the defining contrast in this case, since we are using ABCD since we are going to confound with ABCD, then our defining contrast is L is equal to x1 plus x2 plus x3 plus x4. x1 corresponds to A, x2 corresponds to B, x3 corresponds to C, and x4 corresponds to D. Okay, now let's generate the blocks. Okay, so again, let's to make it easier, let's represent, okay, in ones and zeros the different treatment combinations. So you have 1, A, B, C, and so on. Okay, and their corresponding linear combination would be as such. Okay, as I've shown you before. All right. So for 1, you have 1 times 0 plus 1 times 0 plus 1 times 0 plus 1 times 0. That would be 0. So for example, ABC. Let's take another one. ABC. Okay. 1 times you have high level of A. So 1 plus 1 times 1 also for B, plus 1 times, you have C there, so times 1, plus 1 times 0 because you have low level of D in this treatment combination. And that would be equal to 3. And this is actually equal to 1 modulus 2. Now, if we complete the list, okay, you would have two groups of combinations, okay, having the same L modulus 2. Okay, and those that have the same L modulus 2 would belong to one block and then the rest to the other. Okay. Now, further modification. Okay, let's look at further modification. Suppose that the raw material used to run one block, okay, is inferior, okay, causing responses to be 20 units lower in this block. Okay. Now, in practice, this could be done when it is known that the raw materials or resources have expected variations. No. All right. So this is a geometric representation of the block assignment, okay, and say that these are the observed values, okay, for the different treatment combinations, okay. Note that for this example, okay, the main objective is actually to show you, okay, the importance of blocking, okay, in this case. Okay, but for this example, the observations were taken as the difference between the original values, okay, in the original example, and 20, because in our modification, we are to suppose that the other batch of raw material would result in inferior performance with 20 units lower in one block. Okay, therefore this was originally 45. Okay, so minus 20, it became 25. Okay, for purposes of illustration. Okay, so all of these values are 20 units lower. The block effect can be computed simply as the difference between the means of the two blocks, the mean of the observations between the two blocks. So in our case, the mean for block 1 is 406 over 8, and that for block 2 is 555 over 8. Okay, and this is equal to negative 149 over 8, or negative 18.625. 0.625. And this means that block 1, okay, the mean of block 1, okay, is about 19 units lower than block 2. Okay. Now, to obtain the sum of square for the blocks, again, we just get the square, the sum of the square of the sums. Okay. We square to obtain the sum of square of the blocks, okay, we use the familiar expression. Okay, so we have we square, okay, the sum of the observations per block, okay, and then we get the sum of that. Divide that by 8, okay, minus the square of the grand total divided by 16, and so that would be this number. Now, remember that for the main effects and the interactions, they are computed in the same manner as when you are not actually performing blocking. Okay, so again, so for A, B, C, D, and the interactions, so the effects here would be the same as in the case where you are actually not blocking. Okay, now of course we have an added row here, okay, which is the block, and we know that the block is confounded with A, B, C, D. Okay, and this remember that this is the sum of square that we just computed earlier. Okay. Okay, now to make the point on the use of blocking, now let's focus on this number here, negative 18.625. Okay. Now, this value is actually equal to the effect estimate for the interaction of ABCD plus the effect of the block. Okay, so this negative 18.625 is actually the sum of the original ABCD effect estimate, which is 1.375, okay, if you recall the previous example, plus the block effect, okay, and the block effect, okay, is actually the 20 units, okay, because of the performance, the poorer performance of the batch of raw material that was used for one block. All right, and 20 plus 1.375 is negative 18.625. Okay, with ABCD being confounded with the block, okay, the effect of the block is captured and it is aggregated with the effect of ABCD. Let's look at the Anova table. Okay, as you can see here, we have still AC and AD as the significant effects, and then we have block here, and then your error, okay, and the total. The results are basically the same, no? But if we didn't perform blocking here, the results would have been very different. Okay, so always remember that blocking is a very important tool to reduce noise in your experiment. So always consider the presence of nuisance factors and therefore noise, and when in doubt, perform blocking in order to reduce potential noise. So to further illustrate the importance of blocking, okay, let's compare the results from the experiment, from the design where we had the blocking and one where no blocking is performed. So say for example that we just ran the experiment as though we just ran the experiment as shown here, okay. The results, okay, would actually be similar, but AD will not be found significant, okay. And we know that the finding that AD is significant was actually key in answering the original problem in this example, okay. So because blocking, okay, was not performed, that important finding was not found in this experiment, okay. So we have to note that blocking is an important noise reduction technique, okay, and not blocking may result in noise being distributed across the design factors and some in the error estimate. So in this case, it was actually distributed to AD, okay, and the error estimate as well. So for example, the residual mean square for this model is about 109, which is much higher than in the model with blocking. Okay, so now let's move on to confounding the 2 to the k factorial design in 4 blocks. So P in this case is equal to 2. Okay, what is the motivation for confounding the 2 to the k factorial design in 4 blocks? Okay, this would be useful when your k is greater than or equal to 4 or is moderately large, okay, and your block sizes are relatively small. Okay, so it would be useful in this case to adopt 2 to the k factorial design confounded in 4 blocks. Okay, and in general, that would be termed as 2 to the k minus 2. Okay, so for example, a 2 to the 5 factorial design where only 8 observations can be run per batch, okay, so 8 observations can be run per block basically, okay, it would be logical to have a 2 to the 5 minus 2 observations in a block, okay, so 2 cubed, right? So you have, with this 2 to the 5 minus 2, you would have 4 blocks, okay, and in total you would have 2 to the 5 observations. So how do you construct the blocks for this 2 to the 5 minus 2 factorial design? So first, you select 2 effects to be confounded. So for example, we select ADE and BCE, okay? Now, this note that this automatically confounds the generalized interaction. And the generalized interaction in this case, since we chose ADE and BCE as the 2 effects to be confounded, is basically the product of ADE and BCE. And that would be A B, C, D, E squared. Okay, and recall that E squared is just equal to I. All right. So we have A, B, C, D. Now, the confounded effects must not be of interest. So you have to take care. You have to be careful that the effects that you choose for confounding the blocks, okay, is not of interest. So, for example, if CE is of interest, then you cannot choose ABCDE and ABD as the two effects that you would confound in the with the blocks, because the generalized interaction of ABCDE and ABD is actually CE. Okay, so A squared, ABCDE times ABD would be equal to A squared, B squared, C, okay, D squared, E, and that would redound to CE. Okay, and if C is of interest, then it would be confounded with the block as well, which is not desired. After selecting the two effects to be confounded, okay, the next thing for us to do is formulate the defining contrast for the confounded effects. So in our example, where we chose AD and BCE to be confounded, L1 corresponding to ADE would be equal to X1, X4, X5. X1 corresponding to A, X4 corresponding to D, and X5 corresponding to E. And then L2, okay, for BCE, okay, would be equal to X2, that corresponds to B, X3 corresponds to C, and X5 corresponds to E. Okay. After formulating the defining contrasts, okay, we can now move on to the generation of the principal block using the two defining contrasts. Okay, I will show that later on. And after that, we generate the other blocks using the group theoretic properties of the principal block. Okay, so we already generated the defining contrast L1 and L2, and we know that our effects to be confounded with the blocks are ADE and BCE. So ADE and BCE. So for L1, okay, looking at treatment combination A, okay, this means that you have high level for factor A. All right. So for our treatment, for our defining contrast, okay, we have X1, X4, X5. So that would be X1, okay, 1 times 1, okay, plus 1 times 0, okay, because we don't have high level of D here, and then plus 1 times 0 because E is also at low level here. So this one is equal to 1, okay, and this is equal to 1 modulus 2. For L2, it would be 1 times 0 plus 1 times 0 plus 1 times 0, and this is equal to 0. And so we have 0, this is 0 modulus 2. Okay? Now, if we do the same for all the other treatment combinations, we would find that that there would be 4 groups, okay, corresponding to the combinations of L1 and L2, okay, taking on either 0 or 1. So for example, for the first group, we would have L1 is equal to 0 and L2 is equal to 0. Second group, L1 is equal to 1, L2 is equal to 0. Third group, L1 is equal to 0, L2 is equal to 1. And then lastly, you have L1 is equal to 1 and L2 is equal to 1 for the fourth group. Okay, and these are the combinations that correspond to these values of the linear combination. So to further show that to you, let's look at this spreadsheet. Okay, so recall that we have a originally we have a 2 to the 5 factorial design, all right? So the treatment combinations corresponding to that factorial design would consist of 1 up to A, B, C, D, E, okay? So we actually have 32 combinations, all right? So because that's 2 to the 5 combinations. So that's a lot of combinations, right? And we note that in our modified example, we can only accommodate eight runs in one batch. That's the reason why we have 4 blocks for this design. Okay, now these are just the table of plus and minuses, okay, for each of these combinations. All right, so I just inputted -1 for low level and +1 for high level. All right, and this is the ones and zeros corresponding to the treatment combinations. All right, and this would be the value, okay, of the defining contrast for each of these combinations. And this is just equal to the sum product of the zeros and ones, okay, and the plus and minuses for each treatment combination. Okay, and this column shows the L1 modulus 2. Now, we can do the same thing for L2, okay, where L2 is x2 plus x3 plus x5, okay, because we confounded BCE, interaction BCE. And then this would be the values for that. Now, okay, let's go back to this first. Okay, so I've shown you the groups for L1 and L2. We have to take note that with 4 blocks, there are actually 3 degrees of freedom. And we've only used 2 degrees of freedom so far, corresponding to ADE and PCE. Now, one more is actually available, and this is used for the generalized interaction. And the generalized interaction for our case is, again, A, B, C, D. Okay? So the principal block can be obtained using group theoretic. Okay. So let's go back to the spreadsheet. In the same manner that we obtained L1 and L2, okay, we can also do the same thing for L3. Okay, so our L3 now, because we have A, B, C, D as another interaction to be confounded with the block, okay, would be x1 plus x2 plus x3 plus x4. Okay, therefore we have 1 for A, 1 for B, 1 for C, 1 for D. All right, and 0 for E. Okay, and these are the zeros and ones corresponding to low and high level for each of treatment combination. Okay, and so we just get the sum product of this and the zeros and ones here as well. Okay, and so we get the value of L3 and then correspondingly the L3 modulus 2. Okay, now in summary, okay, this would be the values of L1 modulus 2, L2 modulus 3, and then L3 modulus 2. Okay, now if we try to group these values, no, we would actually have 4 values. One where all the values are 0 for L1, L2, and L3 modulus 2. And then another group where the values for L2 modulus 2 and L3 modulus 2 are 1. And then another group where you have 1 for L1 modulus 2 and L3 modulus 2. And lastly, 1 for L1 modulus 2 and L2 modulus 2. Okay, and so we have 4 groups. Now with these 4 groups, we can form the 4 blocks. All right. Now alternatively, okay, we can actually use the group theoretic properties of the principal block. Okay, so we can generate the principal block Okay, and that block is the one that contains 1, the treatment combination 1. Okay, and then we can just generate the other components of that block by multiplying any 2 elements, okay, from that block. Okay. Now, the other blocks can actually be obtained by using the principal block and the its group theoretic properties, and that is we can just select one element from the other block and multiply it by each element of the principal block. Okay, so let me illustrate that. Okay, so let's look at this. Okay, so let's illustrate that, the group theoretic properties of the principal block. Okay, so the principal block is this one because it contains the treatment combination where all factors are at a low level. Okay, you will notice that all the other elements can be obtained by multiplying 2 other elements in the principal block. So for example, BC times AD, okay, is equal to ABCD, okay, and ABCD is actually here. And then you can also have ABE times BC, okay, ABE times BC is just equal to ACE, and ACE is also here, and so on. All right. Now for the other blocks, okay, we can just take one element from that block. So for example, B, okay, in the second block, and multiply it by all the elements of the principal block to generate the components of this particular block. So for example, B times 1, B times BC, okay, this is B times 1, this one C is B times BC, okay, B times BC, that would be BC squared, okay, so that would just be B squared C, I should say, and so that would just be C, okay. Now AD times B would be ABD, ABCD times B is just ACD, and so on. All right. Okay, so now let's move on to confounding the 2 to the k factorial design in 2 to the p blocks. So p is less than k, okay, and we have p independent blocks, which means that no effect chosen is the generalized interaction of the others, and each block would contain 2 to the k minus p runs. Okay, so what is the method, the general method for constructing blocks for a confounded 2 to the k factorial design in 2 to the p blocks? Okay, the first thing is of course to select the p effects to be confounded. Okay, so the blocks will also be confounded. Take note that the blocks will also be confounded with the 2 to the p minus 1 generalized interaction. So for example, if ADE and BCE are chosen effects, then ABCD is automatically confounded. That is included in the 2 to the p minus 1 generalized interactions. The confounded effects must not be of interest. So again, care must be taken in choosing the p effects to be confounded. As I mentioned in the previous discussion, if say for example C is of interest, then you should not be choosing A, B, C, D, E, and E, B, D as effects to be confounded with the block. After choosing the effects to be confounded, the next step is to formulate the defining contrast for the confounded effects. Okay, that would be L1 to LP. And then after that, you generate the principal block using the P defining contrasts. And then the fourth step is generate the other blocks using the group theoretic properties, as I explained earlier, of the principal block. Okay, and if you do that, okay, and this table is actually provided by Montgomery as suggested blocking arrangements for the 2 to the k factorial design. So for example, if you have say 6 factors, number of factors, no, and the number of blocks, k, is 2 to the p, where p is less than 6. So say for example, you have two blocks, okay? That means that P is equal to 1, right? Then, and the size of each block is 2 to the k minus P, okay? So, for example, if you have two blocks, then the size of each block would be 32, okay? 32 runs, okay? And the effects chosen to generate the block ideally would be A, B, C, D, E, E, F, okay? And the interactions confounded with blocks would be A, B, C, D, E, F. Okay, so in another example, say for example that you can only run 4, okay, 4 combinations in one block. So that would be 2 to the 2, all right? So k minus p is equal to 2. So 6 minus p is equal to 2, which means that p is equal to 4, right? With p equal to 4, okay, you have to choose 4 effects to confound your blocks with, okay? And this table suggests that you use ABF, ACF, BDF, and DEF. With these effects chosen as the ones to generate the blocks, okay, you would also have to include the interactions, okay? So with these effects, okay, used to generate the blocks and their interactions, these are the overall effects and these are the overall interactions that are confounded with the blocks. Since you have 16 blocks, okay, you would have 15 degrees of freedom, okay? And so this would be in total 15, okay? For this you have 1, this one you have 3, okay? You have 8 blocks here, so you have 7, okay, interactions confounded with blocks for this one, and so on. Okay, now let's talk about how to compute sums of squares for a confounded 2 to the k factorial design in 2 to the p blocks. Okay, the sum of squares of all the effects are computed as if there are no blocks, okay, as I mentioned earlier. And the sum of square of the block is computed by adding the sums of squares of the effects confounded with the blocks. Okay, now let's move on to partial confounding. Now, if there is a prior estimation of error, or when you can assume that certain interactions in your experiment are negligible, then replication may not be necessary. However, when this is not true, when you don't have a prior estimation of the error, or you cannot assume that certain interactions are negligible, then you have to perform replication, okay? So, say for example that you have to replicate in a design where you also have to confound, okay? Where you also have to confound because the number of the resources, okay, are not enough to run a complete replicate, okay? The advice in this situation, or the recommended approach in this situation is what we call partial confounding, okay? And of course, we do replication to enable the estimation of error, okay? Because these two things that I mentioned earlier are do not hold, okay? Now, with partial confounding, okay, we basically choose a different effect to confound in each replicate. So, for example, okay, we have a 2 to the 3 factorial, okay, and then we have 2 blocks and we have 4 replicates. Okay, so replicate 1, 2, 3, and 4. As you can see here, illustrated in this figure, we have a different effect confounded in each replicate, okay? Now, in this case, there's what we call relative information for the confounded effects. So, since we have 4 replicates, we have 3/4 relative information for the confounded effects. Okay, so because for replicates 2, 3, and 4, for example, we can actually derive information about ABC because it is not confounded in these replicates. For AB, we have 3/4 relative information from replicate 1, 3, and replicate 4, and so on. Okay, and this shows us the ANOVA for partially confounded 2 to the 3 factorial design. These are the sources of variation. Okay, so again, you have your main effects, you have your interactions, okay, and AB, for the interactions, you have to obtain from the replicates where you did not confound that particular interaction. So for example, for AB, the estimate for this source of variation would be obtained from replicates 1, 3, and 4 because AB was confounded in replicate 2. Okay, and so on. Now, we also have to include, okay, the replicates as a source of variation, as well as the blocks within the replicates, because we have an incomplete, because we don't have enough resources to run a complete replicate, right? So we had to block, okay, blocks within replicates, okay, and the error sum of squares, okay, actually contains the replicates times the main effects, okay, main effect sum of squares, plus the replicates times the interaction sum of squares of each replicate in which the interaction is not confounded, okay. So since we have 8 blocks, okay, we have 8 blocks, we actually have 7 degrees of freedom. So 3 of which correspond to the replicates, okay? And then 4 correspond to the blocks within the replicates. Okay, so let's illustrate that with an example. So first, let's recall an original example from previous lectures, the nitride etch process example. A 2 to the 3 factorial design was used to develop a nitride etch process on a single wafer plasma etching tool. The design factors are the gap between the electrodes, the gas flow, okay, and the RF power applied to the cathode. Each factor is run at 2 levels and the design is replicated twice. The response variable is the etch rate for silicon nitride, and the etch rate data are shown in the following table. Okay, so these are the values for the different combinations. Okay, so you have 2 replicates. Okay, and this was the original geometric representation for this experiment. Now, these are the modifications. Okay, so suppose that only 4 treatment combinations can be tested in a shift. Okay, and of course, since we have a 2 to the 3 factorial design, a complete replicate needs 8 runs, okay, here. All right, so we need 8 runs, right? And we can only run 4 of these 8 runs in one shift. Okay, now there is a potential shift-to-shift difference in etching tool performance. Therefore, it is logical to have the shift, okay, represent a block to reduce the noise contributed by this factor. And replicate 1 can be confounded with ABC, okay, and then replicate 2 can be confounded with AB, okay. So these are the higher order interactions. Okay, so with these chosen effects to be confounded with the blocks, okay, we could generate these 2 blocks with the following treatments to be run in each block. Okay, so for example, for replicate 1, ABC confounded, okay, we would have these treatments, okay, in block 1 and these treatments in block 2. And then replicate 2, we have a different treatment. We have a different effect being confounded, that is AB, okay, and therefore we would have these combinations to be run in these 2 blocks. Since we have 2 different effects being confounded, then we have what we call a partially confounded factorial design, okay, in 2 blocks. Okay, now how do we compute for the sums of squares, okay, of confounded effects, specifically in this case for the partially confounded design for this example? So we get the sum of square for ABC, okay, from the block where it is not confounded, okay? And we also get the sum of square for AB from the block where it is also not confounded, okay? So for SSABC, okay, this is again the original expression for computing for this effect, ABC, okay? And we get the values from the block where it is not confounded, okay? So let's go back to that. The block where it is not confounded is replicate, the replicate where it is not confounded is replicate 2, I should say, okay? And these are the observations, 604, 1052, and so on, okay? And that's why you have this 604, 1052, and all the other values there, squared, okay? Divided by 1 times 8, that would be this value. And then for sum of square AB, okay, we use this equation, okay? We use this equation and we use the values from replicate 1 because AB is not confounded in replicate 1, and this would be the set of values. Okay, so you see these values here, and we get 3,528. Okay, now the other effects will be sum of squares for the other effects will be computed as though there is no blocking. Okay, and again, the sum of square of the confounded effects are only computed using data from replicates where they are not confounded, as we have discussed. Okay, another thing that we have to compute for is the sum of square of the replicates. Okay, and this is equal to the summation of RH squared over 2 to the k minus the grand total squared over n. Okay, where R sub h is equal to the total observations in the H replicate. So for example, for the first replicate, okay, the total of observations is 6,084 squared, plus the second replicate, the total observations is 6,333, and then we square that. We divided by that by 2 to the k is equal to 3, so 2 to the 3, which is equal to 8. Okay, and then subtract the square of the grand total divided by the number of observations, which is 16. Total number of observations. Okay, and we get sum of square for the replicate equal to 3,875 approximately. Okay, and then now to compute for the sum of square of the blocks, okay, we basically add, okay, the sum of square of the two confounded effects. Okay, so from replicate 1 and from replicate 2. So SSAB, ABC plus SSAB, and this is equal to 458.125. Okay, so take note that in this case, okay, for computing for the sum of square of the block, okay, we are obtaining the sum of square of ABC from replicate 1, okay, and then the sum of square of AB from replicate 2. Okay, so given all those estimations, we can form the Anova table. Okay, and based on the Anova table, factors A, C, and the interaction AC are the significant sources of variation. Okay, and again, this is an example of 2 to the 3 design with partial confounding. Okay, so that's the end of our lecture. For this lecture, these are the things that we have discussed. First, we talked about blocking a replicated 2 to the k factorial design. And then we talked about confounding in the 2 to the k factorial design. This discussion included the motivation and the implications of confounding. And then we also talked about methods for constructing the blocks, as well as how to analyze confounding into the 2 to the k factorial design. In particular, we talked about 2 blocks, 4 blocks, and then the general case 2 to the p blocks. And then lastly, we talked about partial confounding, its motivation, and how to analyze this kind of design. So that's the end of Unit 2-3. Okay, we will move on to fractional factorial design in Unit 2-4.